In this video, let's understand the concept of discrete time derivative pricing, comprehensive guide to implementing the binomial model from first principles. The valuation of financial derivatives is one of the cornerstones of modern quantitative finance. At its heart, this discipline is not about forecasting the future, but about determining a fair price for a contingent claim relative to the known price of its underlying asset. This process is made possible by a powerful set of economic principles, chief among them the principle of no arbitrage. The no arbitrage principle is the central axiom of asset pricing theory. It asserts that in an efficient market, there are no opportunities to make a risk free profit with zero initial investment. An arbitrage opportunity, often described as a money machine, would exist if an asset could be bought and sold simultaneously at different prices, or if a portfolio could be constructed that costs nothing and has no possibility of a future loss and a positive probability of a future gain. In practice, such opportunities are exceedingly rare and short lived. The collective actions of traders swiftly eliminate any price discrepancies. For example, if a stock is cheaper on one exchange than another, arbitrageurs will buy the cheaper stock and sell the more expensive one, causing the prices to converge until the opportunity vanishes. The binomial model is constructed from the ground up to be explicitly free from arbitrage, which is what gives its pricing results the theoretical validity. This principle transforms option pricing from a speculative guessing game into a deterministic problem of relative valuation. The mechanism that enforces the no arbitrage condition is the concept of replication of a portfolio. This is the crucial idea that the exact payoff of a derivative security can be perfectly duplicated or replicated by a dynamically managed portfolio consisting of a specific quantity of the underlying asset and a certain amount of borrowing or lending at the risk free rate. Consider a simple one period world where a stock with the price S can only move in two states, up or down, where the up state is denoted by SU and the down state is denoted by ST. An option on the stock will have a corresponding payoff in each state equal to CU and CD. To replicate these payoffs, one can construct a portfolio by purchasing delta shares of the stock and borrowing an amount B at a risk-free rate R. The value of this portfolio must match the options payoff in both future states, leading to a system of two linear equations. The equation for the up state is equals to delta SU plus B into e to the power of R delta T, and this should be equal to the option payoff of the up state. And the linear equation for the down state is delta st plus b to the power b into e to the power of r delta t should be equal to the option payoff of the down state. Solving this system yields unique values for delta and b, which is the amount to borrow or lend. Because this portfolio perfectly replicates the options future cash flows, the no arbitrage principle dictates that the options price today must be equal to the cost of creating this portfolio. Therefore, C should be equal to delta S plus B. If the options market price were to deviate from this value, an immediate and riskless profit could be made by buying the cheaper instrument and selling the more expensive one. While financial markets operate in continuous time, a practical model often requires a discrete framework of computation. The binomial model provides such framework by representing the potential evolution of an asset's price as a series of discrete steps. This construction is not arbitrary. It is a carefully designed numerical approximation of the continuous time model that has become the industry standard for asset price dynamics, the geometric Brownian motion. The Black-Scholes model assumes that the asset prices follow a stochastic process known as the geometric Brownian motion. The process is described by the following STE. dST is equals to U into ST into dt plus sigma into ST into dBT, where U is the expected rate of return, also called the drift, and sigma is the volatility of the asset's returns. And dBT is the increment of a Wiener process, representing the randomness. U into ST into dt represents the drift term, whereas sigma into ST into dWT captures its random and unpredictable fluctuations. A key property of GBM is that it implies that the asset prices are log normally distributed, meaning that the natural logarithm of the price is normally distributed. This ensures that the asset price can never become negative, a crucial feature for modeling financial asset prices. The binomial model is fundamentally a discrete time method designed to approximate the continuous GBM process. Now let's look into the construction of the lattice. The binomial model approximates the continuous part of GBM with a discrete lattice or tree of nodes. Each node represents a possible asset price at a specific point in time. To ensure this approximation is both computationally efficient and theoretically sound, John Cox, Stephen Ross, and Mark Rubinstein in 1979 proposed a specific set of parameters for constructing the tree. This is called the CRR method after the names Cox, Ross, and Rubinstein. If we are given a total time to maturity t and a number of discrete steps as n, the parameters are defined as time step duration or delta t is equals to overall time to maturity by the number of discrete steps. The up factor u, which describes the multiplicative factor for an upward price movement in one time step, is equal to e to the power of sigma into root of delta t. The down factor or the multiplicative factor for a downward price movement d is equals to e to the power of minus sigma into root over of delta t and can also be written as 1 by u. The risk neutral probability p, which is the probability of an up move in the risk neutral world, is equals to p is equals to e to the power of r delta t minus t whole by u minus t. So a simple one period binomial lattice will be somewhere like this, where S naught is the initial price and P is the probability that the price will go up, and 1 minus P is the probability that the price will go down. And U S naught is the price at the upstate, and D S naught is the price at the downstate. This specific parameterization is critical. The condition D is equals to 1 by U ensures that the tree is recombining, meaning an up move followed by a down move results in the same price as a down move followed by an up move, which means that this down move and this up move will coincide to the same price. This property is essential for keeping the model computationally tractable. Now let's look at the pricing algorithm of the derivatives. The valuation of an option using the binomial lattice is a two-stage computational process. First, the complete set of all possible future asset prices is generated in a forward-moving step. Second, the option's value is calculated at each step of these price sprints, starting at the expiration and working backwards through the tree to the present day. The first stage of pricing, or the forward propagation stage, involves building the entire lattice of all possible future stocks. This process begins at time zero with the known current stock price S naught, which forms the root node of the tree. From this starting point, the prices at all subsequent nodes are calculated systematically. At any given node I, j, the formula of the stock price Sij is equals to S naught into u to the power of j into d to the power of I minus j, where j is equals to the number of up steps taken from the time zero. This forward propagation maps out the entire state space of the underlying asset consistent with the given volatility and time horizon. It does not predict which path the asset price will take, but rather generates all possible paths required for the subsequent valuation stage. With the asset price fully constructed, the valuation of the option begins. This stage is called the backward induction stage. This is a recursive process, a form of dynamic programming that starts at the final step and works backward to time zero. The first step of backward propagation is valuation of the option at the expiry. That is, t is equals to t, which is the end time. The process starts at the terminal nodes of the tree. At each of these nodes, the option's value is simply its intrinsic value, as there is no remaining time. So for a call option, Ct is equals to max of 0, st minus k. And for a put option, Pt is equals to max of 0, k minus st. After this, we start the valuation of the prior nodes. For each node at the prior time step t, which is less than the time to maturity, the option's value is calculated as the discounted expected value of the option in the subsequent period, which is that is the discounted price of t plus delta t. The expectation is taken using the risk neutral probability p, and the formula for the option value at any node is given as Vt is equals to e to the power of minus r into delta t whole into p into v up at the next state plus 1 minus p into v down at the next state. where P is the probability of the stock moving up and 1 minus P is the probability of the stock moving down. This recursive calculation is repeated, moving one step backward at a time until the root node at time 0 is reached. The value at this initial step, V0, is the arbitrage-free pricing of the option. A significant advantage of the binomial model is its inherent flexibility to price American-style options, which can be exercised at any point before or at expiration. The backward induction algorithm is easily modified to accommodate this early exercise feature. At each node during the backward pass, a decision must be made. The holder of an American option can either hold it for at least one more period, or call the continuation value, or exercise it immediately at the intrinsic value of that current period. The options value at the node will be the greater of these two choices. So the modified formula for VT for an American option is equals to max of intrinsic value, comma, continuation value, where the continuation value is standard discounted expected value calculated for an European option. This comparison is performed at every node in the tree. If the intrinsic value is higher, it means early exercise is optimal at the specific price and time, and that value replaces the continuation value at that node. This potential for early exercise means an American option can be more valuable than its European counterpart. The difference is known as the early exercise premium. This feature is particularly valuable for American put options, which may be exercised early when deep in the money, or for American call options on dividend paying stocks, where exercising just before an ex dividend date can be optimal to capture the dividend payment. The computational efficiency of this entire backward induction algorithm hinges on the recombining nature of the asset price tree. If the tree were non-recombining, the number of nodes at step n would be 2n, making the calculation intractable for even a modest number of steps. For example, a 30-step tree would have over a billion terminal nodes. However, because the CRR parameterization with D is equals to 1 by U ensures that the tree recombines, the number of unique nodes at each step I is only I plus 1. The total number of nodes in the tree grows quadratically proportional to n square, not exponentially. This transforms the binomial method from a theoretical curiosity into a powerful and practical pricing tool. Now let's look into the complete Python implementation of this from scratch. This section translates the theoretical framework into a practical and efficient Python implementation using an object-oriented approach and the NumPy library for vectorized calculations. We built a reusable class capable of pricing both European and American options. The implementation requires only the NumPy library for numerical operations. The model itself is defined by a set of core parameters: the initial stock price S0, the options strike price K, the time to expiration in years T, the continuous compounded risk-free interest rate R, the asset's volatility sigma, and the number of time steps in the lattice N. Additional parameters will specify the option type, call or put, and exercise style, European or American. To encapsulate this model's logic cleanly, we defined a class named Binomial Option Pricer. This class will store the input parameters and contains the methods necessary to build the trees and compute the option prices. The implementation will demonstrate a professional quant-level approach by leveraging NumPy's array operations to avoid slow explicit loops in Python wherever possible. The following code represents the complete binomial option pricer class. The implementation is heavily commented to link each step back to the theory and for easy understanding, because sometimes when we explain the code, we might miss out a few things. This code resource will be linked in the description for replication if needed. So first, this init function initializes the parameters and sets up the whole state space for the binomial lattice. This function is to set up the parameters like dt, u, and d, and p, and this const factor. This function is used to perform the forward propagation to build the stock price tree. The tree is stored in a NumPy array. Now, this function initializes the option value tree with payoffs at maturity. And this is the function we use to perform the backward induction to calculate the option values at each node. And this is the result function which returns the calculated option price at time zero. Let's populate the parameters of this class by calling this class with an S naught is equals to 100 and K is equals to 100 and time to maturity is 1 year and R is equals to 0.05 and sigma or volatility equal to 20% and number of steps is equals to 100. Now, if we run this code, the value of the European call price which we got is equals to 10.4306 and the value of the European put price we got is 5.5536. The value of the American call price is 10.4306 and the value of the American put price is equals to 6.0824. You can see there is a slight increase in the value of the put price of the American put option. This result aligns with the financial theory. The American call on non-dividend paying stock has no early exercise premium, so its price is identical to the European call. In contrast, the American put is more valuable than the European counterpart, reflecting the value of early exercise right. The binomial model, while powerful in its discrete framework, is deeply connected to the continuous time world of the Black-Scholes model. Now, the final code section in this file synthesizes the preceding analysis by demonstrating this connection, showing how the binomial price converges to the BCM price and clarifying the role of each model. Fundamental result in the financial theory is that as a number of steps n in the Cox-Ross-Rubinstein binomial model approaches infinity, the price of the European option calculated by the model converges to the price given by the continuous time BSM formula. The BSM model provides a closed-form analytical solution for the European option prices. Now, this is a function which calculates the Black-Scholes price for an European option. To demonstrate the convergence empirically, we can price a European call option using the binomial model with an increasing number of steps and compare the result to the BSM price. After running these code snippets, we got a result something similar to this. So the Black-Scholes call price for these parameters is given as 10.4506. And if you look at the binomial price convergence, we can see that as the number of n increases, the difference in the price between the Black-Scholes price and the binomial lattice decreases, providing a powerful numerical confirmation of the underlying theory. This relationship reveals a deeper truth. The binomial model is not just an approximation of the BSM formula, but rather a numerical solution to the underlying Black-Scholes partial differential equation. The BSM derivation results in a PDE that governs the price of any derivative of an asset following the GBM. While the PDE can be solved analytically for simple European options, it becomes intractable for options with complex features like the early exercise option or the American option. The backward induction algorithm of the binomial model is in fact a numerical technique known as the explicit finite difference method applied to solve this fundamental PDE. This is why the model can handle American options. It solves the pricing equation step by step, allowing it to incorporate the max of intrinsic comma continuation logic at each node, a condition which is difficult to capture in a single closed form solution. This reframes the binomial model from a simple alternative into a general and powerful numerical solver at the core of the computational finance. In conclusion, the binomial model serves as both a foundational pedagogical tool and a versatile practical pricing engine. It makes the abstract principles of no arbitrage and replication tangible through its intuitive lattice structure. While the BSM model offers an unparalleled speed and elegance for the standard European options, the binomial model's discrete, iterative nature provides the flexibility required to tackle the complexities of an American option or early exercise options and exotic derivatives, securing its place as an essential component of quantitative finance. Thank you.